Okay, let's begin our discussion for the fourth session out of what we are simply recording and uploading. Uh, let's see. I think we pretty much discussed resource allocation procedure. The major difference uh, from LT, you can have semi-persistent uh, scheduling, especially for voice type of application. And instead of VOLT, now you call it VONR, voice over NR. Okay, so I mean, we keep the periodicity, okay, how, how, how much will be the interval between the packets. It's called vocoder, which generates the packets out of voice we speak. They convert it into digital bits, okay, uh, after some compression and all that. And this packets of bits generated by the stage is called vocoder. So some discussion on this DMRS. So the flow of data uses the different layers in the protocol stack, and we mentioned before that there could be distributed unit and centralized unit. Optionally, you can have the base station activities. You can split. You can it's just one central unit and many different distributed units on that. So the activities you can split. And we also mentioned before that this is sort of similar with the 3G 3G days. In 3G, uh, there is a node RNC, okay, under which you have the different base stations. And then you also had the implementation split. Like in that case, the base station uh, processed on up to the MAC layer. I mean, the physical layer and the MAC layer was processed at the uh, base station. And RLC and PDCP. SDAP was not there. RLC and PDCP. In fact, PDCP was also not absent in the early 3G days. Okay. Much later. Okay. Much later, PDCP layer was added to 3G. But anyway, RLC and PDCP is implemented in RNC. Okay. That's also part of radio access network. But at the back end, we have RNC, and RNC have many bases. Now, in this case, in 5G, when you split, you implement up to RLC in your distributed unit, and you now have SDAP2. It is SDAP is implemented in centralized unit. SDAP layer increases the uh, and, convenience in handling different types of uh, qual- quality of services. Now we know that. I mean, I mentioned several times that if you have a different quality of service requirement, then you need a different data flow pipe. Uh, if you have that, and there can be many different options now in 5G to better handle the different DRBs, uh, each of which relates to a particular QoS or data profile. This SDAP layer is added. Like you add some identity for a particular QoS. Okay. So discuss QS flow. I mean, data flow pipe with a certain QS flow. You have some identity for that QF5. We may not go to too much details. The activities of other layers, BTCP, RSC, are very similar. Okay. As you have, I don't see any changes there. Okay. And so instead of learning from here, you had better uh, learn from my book if you are interested. We're not discussing the activities of different layers in detail. BTCP, uh, RLC, and NAC here. But my book explains these activities the best. Uh, do you guys know why I praise myself? Uh, I praise myself because other people don't do that. They don't praise me, and since they are not fulfilling their responsibilities, okay, I have to do it myself. Uh, so anyway, chapter 6, 7, and 8 in my book explains the activities of MacLayer, RLC, and PDC in detail. You'll find the detail of these actions. RLC has three modes: TM, UM, and AM. The transparent mode is not used for data. I never mentioned this mode, but it is also there in LT. In 5, 5G or LT, you have seen the same type of modes and their activities. And as you can see, this is the user data channel. It's the logical layer when you go upwards in defining the layers. So the, this data transfer layer uses either UM or AM, depending on whether it's error sensitive or error tolerant application. Now you see this TM is used only for BCCH, which includes the system information messages. Okay. In TM or transparent mode, you actually don't do anything. Your UM or EA modes, you chop the packets into pieces and add headers to them. Especially for A, you have log and header. But in TM, you don't do anything. You just forward the packet. So it's called transparent mode. But it is not used. It is just used for control plane. You see, the RLC, TM RLC is applicable on control plane. Okay, so out of back layer activities, we discussed only HARQ. Uh, say power headroom, BSR, the buffer status report. This buffer status report we discussed. We will also talk about the use of power headroom in back layer. But now I'll talk about let's see what we have next. I've selected a few pages, but we're not discussing everything of the pages I've shared. Okay. I just wanted to make your content, your 5G stuff, okay, more resourceful or uh, it can be reached, although our discussion is limited. Okay. I mean, it's now discussing the allocation for uplink resources, and similarly, we allocate in frequency domain and in time frequency, in time domain, a number of symbols, okay, and then let's see, a starting symbol and the number of symbols. and in frequency domain you indicate the number of resource blocks, okay, 20 kilohertz, 20 subcarriers. The cell reselection and handover procedure looks the same, but the small difference is that now you have RC inactive state in addition to RC ideal and corrected state. Now you have also inactive state. In this inactive state, you perform cell reselection. Okay. And the term you use when you are in RC inactive state, okay, the area which is used for paging is called notification area, as we discussed when we were discussing uh, the inactive state. And I mean, theoretically, it can be a little different, the notification area. I mean, in the inactive state, the area for paging and paging purpose can be a little different from RC active state. Okay, the use of different seeds for information of cell selection. Okay, in this regard, let me tell you that I received a question from one of you that when I was discussing cell selection or LT, I mean, somehow my voice was not enough clear, and yeah, definitely it wasn't. I take that. So what I was saying that CPEC 3. Okay, now I'm talking about LT. Now I'm referring to that discussion. It's a discussion on December 15th, around minute 45. Okay. So I was saying that what I wanted to mean is SIPTET 3 to SIPTET 8, okay, carry information uh, which are necessary for mobility. Okay, salary selection or handover. You need there's the mobility. Okay, to change your cells. So you need different parameter values for this purpose. And SIPTET 3 to SIPTET 8 includes information that is useful for mobility. However, SIPTET 4 through SIPTET 8 are more specific to parameters for different types of RAT. By RAT, I mean radius access technology, I mean different generations. Uh, so SIPTET 5, so I mean SIPTET 3 and SIPTET 4. SIPTET 3 includes different information of the current cell. SIPTET 4 includes different information like what you, say some cells can be blocked. Okay. So this type of information is available on SIPTET 4. So, but SIPTET 4 through SIPTET 8 purely carries information. You have information dedicated for a particular type of RAM. Like, let's go from the end. SIPTET 8 carries information for CDMA 2000, okay, or 3GPP2 type of technologies. It's also possible that you switch to you have cell reselection or handover between 3GPP2 cell and LT cell. Okay. So that 3GPP, I mean, information for 3GPP2 cell types are included in SIPTET 8, and SIPTET 8 is dedicated for this purpose. SIPTET 7 is dedicated to carry information for EMTS cells. Okay. There is no other purpose for SIPTET 7. SIPTET 6 is has dedicated information for 2G cells, I mean DSM, DPRSH. SIPTET 5 is dedicated for interfrequency LT cells. LT cells which are using are different frequencies. Anyway, similar uh, type of I mean, distribution of information. We also have in 5G, but we're not discussing in detail. We will now talk about hierarchy procedure. Okay. Here also the flexibility has been enhanced. Remember, in the case of downlink hierarchy, we had the flexibility. In the case of LTE, that it was adaptive. There are two things: synchronous, whether it is synchronous or asynchronous, and secondly, whether it is adaptive or non-adaptive. When you say the retransmitted block, if it is if it has fixed timing, then it is synchronous. But if you uh, nature the timing or you use the allocation overhead, okay, actually use PDCC, which indicates the time of your retransmitted block. Then you are actually using asynchronous HRQ retransmission. Now we found that in downlink it was asynchronous, but in uplink it is synchronous. The advantage of synchronous transmission is that the overhead is reduced. In the uplink, actually there is no PDCH for retransmission. So it was also non-adaptive typically for uplink. Okay, since you're avoiding PDCH allocation for your retransmitted block, it is non-adaptive. So normally you cannot change your modulation level, your frequency position in the frequency. You cannot change redundancy version. You cannot change any of them. Redundancy version will follow the order first one, then two, then three. And in the case of downlink, you could change. You could change the modulation order. Okay. You could change the frequency position. And the timing you can change already. So it was adaptive. You could change frequency position. Okay. So depending on your new requirement at the time of your retransmission, you can set new frequency position. You can use different modulation order. Okay. Meaning that you can use different amount of resource blocks when you're changing your modulation order. You are also changing the amount of resource blocks. Okay. So this flexibility was there for downlink. Now in the case of 5G, you have this flexibility for both downlink and uplink. I mean, in uplink also, it is asynchronous, it is adaptive. So there is no uh, synchronous or non-adaptive HRQ retransmission in 5G. However, let me uh, remind that in LTE, non-adaptive retransmission was possible in uplink, where you could change two things: the frequency position and the redundancy version. The modulation order you can change. And probably remember that in retransmission, I mean the MCS table, the last the last three, I mean 29, 30, and 31, these three values of MCS was used to indicate the redundancy version for HRQ retransmission, adaptive HRQ retransmission uplink. In that case, of course, you have to use PDCC. So the MCS on PDCC would indicate the redundancy version. And the frequency allocation you can also change on the PDCC. And probably also can remember that in downlink, when you retransmit, the last few MCS fields were used to indicate the modulation order for the retransmitted block. Okay. So if you use up to 2024 far, then actually you need the last 5 MCS values for the indication of modulation, the retransmission. And the rest, 70 is for the normal allocation. Okay. So probably it's clear that it's now HRQ. So the field NDI, okay, uh, here indicates whether or not you have transmission or retransmission, new transmission or retransmission. Also, the HRQ ID, okay, the HRQ ID, you did indicate HRQ process number would indicate. But this process number has a wider range now. Now, the we had a maximum value of 8 for HRQ ID in LT. It was because the round trip time would accommodate a maximum of 4 HRQ processes, right? Probably remember, considering the processing time and the propagation delay. But in 5G, the processes can be faster. I mean, the support of our circuit is now faster. Okay, so the processing time is less. Also, we already discussed that the symbol period, okay, or the time for transmission can be actually shorter for your original transmission. Okay. So the propagation delay is not different. That can also be different for a small cell. 5G, as we grow in generations, we have the cell size smaller and smaller. So in all this respect, you have shorter round trip time, and so you can accommodate actually more HRQ process, and that's why the HRQ process there can be at most 16 HRQ process. So you have HRQ process number where it's 4 bits and it ranges from 0 to 15. Uh, the downlink HRQ. Okay. Another difference is that you don't have to transmit the whole transport block. Okay. Uh, see, we probably discussed before that the transport block is split into small code blocks for the coding purpose. The coding process has a maximum length which it can handle efficiently. And that is pretty small, a few thousand bits. Okay, so like around 8,000 or something. Uh, now, it depends on the coding technique. Now, you you see, I mean, around 8,000 for one type of NTPC use, and for this other type, 4,000. Anyway, so in case of uh, normal HRQ, the a few bits can be in error in some of this code block. Okay? But you have to retransmit the whole transport block because I mean the receiver can actually recognize that only these code blocks are in error. It failed to recover, say, the code block number 10, 15, and 20. But it the whole transport block it will ask for retransmission. It's because it for ACK or NAC it has a single bit. This is just a single bit it indicates, and that single bit indicates the status of the whole transport block, whether it should be transmitted or transmitted. So it can be more efficient if it is if you just it could be more efficient for retransmission if you could indicate which resource code blocks are in error, so just the 10, 15, and 20, then only those code blocks could be retransmitted, and that would need less resources for retransmission. But that's not possible because then for every code block you have to send ACK or NACK, then ACK overhead gets too much. Okay. So 5G introduces a solution which is something in between. It creates some code block groups within your transport block. And for each of the blue CBG or code block group, it sends some ACK feedback. Okay. So it's like this. The transport block is split into a number of code blocks. And you see code block group 1. There are so many code blocks, but you have created 4 code block groups. For each of the group, you send a bit on ACK. So now in 5G, your ACK is not single bit, it is multi-bit feedback, but this multi-bit feedback does not have too many bits, not as many as you have, uh, uh, not as many as the code blocks you have, okay? Rather as many code block groups you have. So that may be just a few. So a few bits you need on ACK. And the HARQ retransmission, I told you that uses a number of versions, okay, and it is shown on a circular buffer. And for theoretical understanding, uh, the first part includes the most important bits. I can find out, and these are called systematic bits. Okay, I mean this is mostly from your original packet. These are called systematic bits. So in the first transmission, you mostly have a system. Yeah, you see, the blue part is called systematic bits. So you see, I mean, this is RV0. This is for original transmission. First, in the first transmission, you use RV0. If you, I mean, that uh, is supposed to help you recover the whole packet, but if not, it's in RV1, which also includes a good part of some systematic bits. So anyway, I mean, all these bits are this. I mean, what bits are really generated out of the original packet? It depends on the coding technique, which is a variation. It can be LDPC, it can be polar, it can be typocoding. Now, I mean, LDPC is the popular technique for 5G. Uh, it has been preferred. Okay, let me wrap up this session. Jazakallah for your time.